Why didn't they put a small roof?
Because they put us over that building. So we needed.
You don't have any other big states. That's the rival building.
Okay. Good morning, everyone. It is my pleasure to introduce our distinguished public lecture by Dr. Gilles Brassard. I think Gilles needs no introduction here. For one thing, he gave a distinguished lecture a few years ago in this very same room. But this time he's in Waterloo to receive an honorary doctorate of the Faculty of Mathematics, which will take place at convocation tomorrow afternoon. So yeah, just in a nutshell, I think Gilles is widely credited as the first to have delved into the field of quantum information science. He's the co-inventor of the BB84, widely used.
If you allow me a small correction, the first computer scientist.
computer scientist, all right.
They were,
Okay.
they were physicists before.
Already started. There you go. Yeah. Yeah. So so the BB84, as many of you know, is widely known and used protocol for quantum key distribution. Holds his name, Bennett and Brassard, 1984, and many other inventions for that matter. He's an officer of the Order of Canada. He's an officier de l'Ordre National du Québec. He received numerous awards, too many to cite, but I mention maybe a few. If I find my paper, here we go. All right, he received the Wolf Prize in Physics, the Mishkish Quantum Prize, the BBVA Foundation Frontiers of Knowledge Award in Basic Science, and the Breakthrough Prize in Fundamental Physics. And most recently, a few months ago, the Turing Award, which, as you know, is the equivalent of the Nobel Prize for Computer Science. And I believe that his talk today has something to do with Turing. So without further ado, please join me in welcoming Gilles to the stage.
Thank you, Robert, for the nice introduction. So in the time remaining, I will tell you about directions, about Turing and me. All right. This, of course, sounds like maybe not the most humble title, but I think I'm allowed in this occasion. Here's Turing. This picture was taken by my wife here in Bletchley Park at the Computing Museum or Cryptanalysis Museum, I don't remember, but somewhere in Bletchley Park where the Allies broke Enigma on a routine basis during the war. So that's a homemade picture. This is an official picture where you see Turing from the top. And what he's holding in his hand, I guess, is an Enigma machine. Of course, a fake one, as a fake Turing. But this is a real one. So here, with the same hand. So here I'm sort of playing with an actual real Turing. So that's my first link with Turing. We both played with these things. That's Bletchley Park. Bletchley Park, where the Allies worked for cryptanalysis during the Second World War. It's very, very nice mansions. You might think, oh, how lucky Turing was to live and work in such a stately place. Not quite. He worked there. There were what they called it huts. There were several huts, HUTS. In Bletchley Park, number 8 was the one in which Turing worked, and that's actually his desk, his office. He really worked there, exactly, during the war. And if you have not visited Bletchley Park, it's really worth it. It's a very nice, very, very, very interesting museum. All right. Now, the more obvious link between Turing and me is not that we both played with Enigma machines. I'm not sure what's playing, but it's this. And even though Raouf was right in saying that this was announced a few months ago, it really was this ceremony, the prize ceremony, took place 3 days ago. So this is a very current picture. You might have noticed there's something fake about this. Not because Turing was not really there, live at least not, but I wasn't there either. The reason is that this took place in San Francisco. And ever since the fascist little dictator in the White House pretends that he can annex Canada as his 51st state, I'm not setting foot into this United States of America anymore. So to me, it's a complete boycott. Complete boycott of travel and even buying spinach. which is really bad because sometimes I have visitors over, I told them to palak paneer. And the only finish I can find is American, so I have to replace them by kale or something. But that's okay. It's a price to pay to be a proud Canadian. So no, I wasn't there. I wasn't. Instead, I was represented by a dear old friend, Brian Barsky. We met at Cornell in our student days 50 years ago. So Brian has been for a long time professor of computer science at UC Berkeley, next door to San Francisco, where the ceremony took place. So Brian agreed to read my speech in my behalf. So that's a real picture. And as you see, Turing was not there. And that's Charlie Bennett, which I got the award, the Turing Award with Charlie Bennett for lifelong collaboration. And he, being American, he had no excuse for not wanting to be there, I suppose. All right. Now the Turing Award was awarded for our essential role in igniting and shaping a quantum revolution in computer science and in information and communication technology. That's the official citation. And you might expect that we'll talk about these things, but no, that'd be too boring. So you might expect we'll talk about quantum cryptography, which is the main reason I got it so far. Of course, the title is Turing and Me, and of course, Turing had to do with cryptography. So if I talked about cryptography, it would be a link with Turing, but not as direct as what I'm going to provide, actually. But I cannot resist showing you the best picture of our BBA for invention, for quantum cryptography, which is this one. So Charlie and me are here in front of a quilt that describes quantum cryptography in a really, really amusing way. And it's in front of a big quilt. This is a big quilt on cryptography in general. You see a padlock here and all sorts of crypto stuff. This is the Alberti's wheel. So all sorts of crypto devices are all around this big quilt. And this is part of an extraordinary scholar called mathematicians, which was designed mostly by a mathematician named Ingrid Novici, who is best known for having invented wavelets. And she was joined by a Quebec textile artist, Dominique Herman, and together they created this is big. This is really very, very big. I should have included a picture of the whole thing. But if you ever have a chance to see mathematicians, which was in Montreal for several months last year, it's worth the trip. And when I was lucky enough to be at the unveiling of this work, for the first public unveiling, which took place at the National Academy of Sciences in Washington in days where it was not indecent to go to the United States. And there it was unveiled and explained by Ingrid and Dominique, very, very lively talk to explain it. So I spent hours going around it, looking it all over. And at the end, I told the two creators, by the way, also about 24 mathematicians who were, it's really a major thing. At the end, I told Ingrid and Dominique, this amazing, this quilt is great. There's only one thing missing. Quantum cryptography wasn't there, among all the little things around it. And I thought it was, no, they took it seriously. And we spent the next 2 or 3 months, we've been them two plus Charlie Bennett designing this quiltlet that was just stitched on. And we were very lucky because if we had been initially there, it would be a very small square. We have a much bigger one. And it looks like this. So where you have fireflies to produce photons and frogs to detect photons. And so we trained the frogs when they see a single photon in their eye to jump up and stick out their tongue so that we can see the photon detection. It's a very convenient apparatus. The point is that it's made of all natural ingredients. Fireflies, of course, and calcite crystals is natural. The only thing maybe not so natural is it has some mirrors here, but except for that, it's completely natural. So when we build that, you might notice not so well here, but that's an ice cube here. The frogs are in iced water with ice cubes because photon detectors were better at cold temperature. We tried to replace the iced water by liquid nitrogen, and for some reason the frogs didn't jump in it. All right, seriously. So no, I'm not going to talk about photography. Okay. However, you might notice here this T-shirt, which I wear. Let's go backside. Well, that's the back of the T-shirt, but I turn it over around so that we can see that for the picture. And that's the drawing the circuit, the quantum circuit for teleportation. So you might think I'm going to talk about teleportation. No. Obviously, this time Turing has nothing to do with it, so it would not be appropriate. All right. How about, well, this is teleportation, but I'm not talking about it. Okay, how about quantum computing? Might talk about that. Clearly, Turing had to do with computing. Not quantum computing, but computing, yes. But no, that's also too boring. So, that's a quantum computer. So this is the IBM version. Just to show you quantum computers, this is an IBM version that works at very low temperature, much lower than nitrogen, by the way. And that's the Chinese quantum computer, which is completely optical. Really amazing. But no, I'm not going to talk about that. All right, so what am I going to talk about? What Turing made. Yeah, specifically, it's a joint work with two former students of mine. And I think this is some of the most, maybe one of the two most fun research I've done. The other one that I'm not going to talk about either because it has nothing to do with Turing is a paper that I wrote with another person of mine on the simulation hypothesis. Do we live in a computer simulation where we give arguments that the answer is no? But that's something else. All right. So, but this I think it's very fun. And that's the paper that it's all about. On computable numbers with application to the Drude problem. Now, Drude problem is a word I invented, even though I don't know any German. When I was told this, okay. But the title is inspired by Turing's most famous paper, his 1936 paper in which he introduced the Turing machine. I'm calling it that, of course, which is this one. So you can see that the title is sort of similar, right? So it's the same, it's just a different application. So Turing's paper is an application to the, this I don't know how to pronounce. And in this paper, in this title, by this title, what Turing made by computable numbers is computable real numbers. So most of the paper is devoted to how to define a computable, how can you say, when can you say that a real number is computable? That was the most important part of the paper, actually. And he introduced the Turing machine to have a formal definition of what computable means. And this thing is a decision problem. Given a mathematical equation, can you always decide if it's true or not? Is it universally valid? Does this Turing machine hold, for instance? And the application to a decision problem was to prove that there are problems that were undecidable. Most of you who've heard anything about Turing or Turing's paper think that in that paper, Turing proved that the whole thing problem is undecidable. And given the Turing machine, will eventually hold on blank thing. And that's undecidable. Great result of theoretical computer science, but it wasn't Turing who proved that. In Turing's paper, he proved something quite different, which implies this. From Turing's actually result, one can easily derive it's what we call the Turing equivalent. We can derive the undecidability of the whole thing problem. But what he proved was somewhat different, because his paper on computable real numbers, so I'm going to show you the actual text in a moment. But intuitively, Turing said that a real number is computable if there is a Turing machine, we did say Turing machine. If there's a Turing machine that can print each digits one by one after the decimal point. So pi is computable because the machine it would print 3, 1, so on. And therefore, what was of interest to Turing was to be able to print all digits to infinity of a real number. Therefore, he was only interested in machines that never, because it would print every digit until the end of time. So the whole thing problem was of no interest to him. So of course, he didn't prove anything, and it's undecidable. But what he proved undecidable is that it's an undecidable of a Turing machine, whose purpose is to print the digits of a number, will at some point print the digit 0. That's what he proved is undecidable. And that's the equivalent to the whole thing problem. All right. So let me show you. Oh yeah, it was a root problem when I invented this for the print problem, which I'm going to introduce. I'm going to tell you what is the print problem in a moment. All right, so here's Turing's paper. That's the first page, first paragraph. The very first paragraph of Turing's 1936 paper, in which he introduces the Turing machine. First sentence, he defines a computable number, by which he means computable real number, as a number whose expression as a decimal or calculable by finite means. That's what I told you. You can print all the decimals one by one. Or equivalently, given n, you can compute the nth digit. It's equivalent. And at the end, he says, well, you use that by definition, a number is computable if its decimal can be written down by a machine. That's the first paragraph. You make a real number, and for the moment between 0 and 1, we will generalize in a moment. So the 0 point, and then the machine would print all digits one by one to infinity. And then the number is computable. That's Turing's definition. And the purpose of my talk is to explain why this is totally inadequate. We will see why. It's not wrong, but it's inadequate. In fact, being able to print all digits one by one is what I would call print problems. I will define it formally in a moment. And this is very important, but Turing used the word decimal, but he's a mathematician, so he read it in binary. But I will work in decimal because it's easier for us humans, intuitively. But except that we work in decimal instead of binary, I'm going to use exactly the definitions that Turing gave. So in more modern terms, or more precise mathematical terms, what it means for number x to be computable in the sense of Turing, which I would call printable, is that taking number x for the moment between 0 and 1 excluded for the moment, we'll generalize it. Define xn by this formula. Now, if you don't like the math, don't worry. All it means is the nth digit of x. In other words, x is 0.x1, x2, x3. It's very easy to see that this would give the x digit. You don't see this. Just understand intuitively what it means. And now, mathematically, it means that x can be expressed as in this form. But this just means that. All right. Now, given any real number between 0 and 1, xn is well defined by this formula. And, well, this formula only works when x is between 0 and 1. But 1 excluded, because if you take x equals 1 in this formula, you will get all zeros. Because 1 is 1.000. Here we have 0 point. Okay. Now it's natural to want to accommodate all real numbers, not only between 0 and 1. And there's no obvious way to do that. The opposite to do that is to add x0. X0 is the integral part of x, integer part. So if you add x0, it's all a. You have xn for all n starting at 1. Xn is the nth digit after this one. If the x0 is the integral part, then the formula works perfectly. It replaces is 1 by 0, and then there you go. So that's the most natural way to define a printable number, which Turing would have called computable, with no restriction of in between 0 and 1. And this formula for some work when it is negative, but it's sort of a mess. So let's not waste our time with negative numbers. Okay, that's, I think, how anybody would do it, but not Turing. You all know Turing was sort of weird sometimes. So guess how Turing did it? So Turing defined what's a computable number, which I call printable. If it's not defined for numbers, real numbers between 0 and 1. And now he wanted to extend that to all real numbers, not only from between 0 and 1. And he did that with this. Well, I'm back to his actual paper. This. So think about it. If this yn, n is not the nth digit. Yn is a computable real number between 0 and 1. So if y, gamma, sorry. So if gamma is a computable real number between 0 and 1, it's a real number between 0 and 1, and you take the tangent of pi times y minus a half, as long as y is not 0 or 1, strictly between 0 and 1, well, then you get a real number like this. So that's a tangent function. And Turing shifted by a half so that it looks nicer like this. So tangent shifted by a half looks like this. So that you see that all real numbers are obtained. And once you know how to do it, real numbers between 0 and 1. That's how Turing did it. Kind of weird. It doesn't really work. And the end, I will tell you why it doesn't really work. Surprisingly, it doesn't work at all, actually. But on the face of it, it seems to. I have no idea why he didn't use the easy way, but that's how he did it. Of course, this definition, as I said before, this is fine as long as gamma is not 0, no, strictly between 0 and 1. If gamma is strictly between 0 and 1, this will define all possible real numbers. So Turing added a special, a special case. If gamma is 0, 1, then he sets the answer to 0. So it's the same format. There's an exception here. It's 0. When it's 0 or 1, the value is 0. But except for that, it's this function. And we'll come back to that at the very end. All right, so here we are. This is Turing's definition, essentially, of a real number between 0 and 1. And then he defines an orbital real number by this formula, with exceptions if x is 0. So that's Turing's definition of a computable real number with no restriction of being between 0 and 1. Very good. Now, I'm going to, as I told you already, to call that a printable number. So here's the complete definition. A real number x is printable if, and I'm going to restrict between 0 and 1 for the moment. If there's a Turing machine or an algorithm that computes x0, which is the integral part, I don't know, not restricted. Any real number will be called printable if there's a Turing machine which can compute an integer part called x0 and the nth digit called xn for each. So give it n, you give this machine as input any number n between 0 and infinity. And if you give it 0, it gives you the integral part. If you give it n bigger than 0, it gives you the nth digit. So if there's a Turing machine that can do that, then the number is printable. That's my definition. Essentially, Turing's definition of computable, except for x0. So that we will have this form. So that this will be true. Very well. Now, I'm going to need a subtlety here, but it's an important subtlety, which is that you might have noticed, I told you before, that with that definition we had so far, if we forget about the tangent thing, if we forget about the integral part, the first definition, that is worth anywhere between 0 included and 1 excluded. Because if you take x equals 1 with this formula, you will get each xi equal to 0. Because 1 is 1 point, 0, 0, 0, 0, 0. So all decimals are zeros. I'm fine here, I can put x 0 equal to 1. But if I don't want to introduce x 0, I have a problem. But many of you, I'm sure, have thought that, well, that's okay, because even without integral part, even without x 0, you can obtain 1 as 0.11111, decimal 0.99999. So the real number 1 can be obtained either as 1.0 to infinity or 0.9999. There are two different decimal expansions for the number 1. In fact, any number, any real number, which is an integer divided by a power of 10, allows two different descriptions. And this will turn out to be extremely crucial. What I define here, explicitly with this formula, will not allow the alternative definition or expansion. So 0.99999 to infinity will never be obtained with this formula for any number x. But we might wish to allow it as well. So if we don't allow it, if we follow this definition, this is what I would actually call, let's give an example first. Pi is printable because, very good. No, so pi is printable. Right. Let's go back here. So I'm going to call this, when I need to address this subtlety of having two different expansions for some numbers, I'm going to call this one strongly, strictly printable. And it's not clear when you read the first paragraph of Turing's paper if he meant that. It's not clear if he would have accepted an infinite sequence of lines at the end. Later it will be clear that he didn't accept it. That's for later. But just from the first paragraph, it's not clear if he would have accepted it. So I cannot tell that this is really, strictly speaking, Turing's definition of what he called computable. So I'm going to introduce weakly printable. Weakly printable means I don't need this formula. Weakly printable means that you can compute the integer part on n equals 0, and you can compute some digit between 0 and 9 for all other inputs, such that this formula applies. So if it's strictly printable, then it's weakly printable by definition because there is formula. But this would allow a number to be weakly printable, even if we accept the alternative expansion ending with infinite many lines. And it's not obvious a priori that these definitions of being weakly or strictly printable are equivalent. It's not obvious at all. So example, 1 is weakly printable. Of course, 1 is strictly printable. But it's also weakly printable in the other way. Okay. Now, the other thing that Turing, one other thing that Turing introduced in his paper is he defined what it means for a function of real numbers and computable. So he defined what it means for a real number to be computable. And he also, in the first paragraph, and then he talked about it at length. He also defined what it means for a function of real numbers to be computable. It's him. A bit later in the paper, where he says, so this is not the first paragraph, despite the appearances. It was the first paragraph. It really was the first paragraph when I showed you before. Now, this is somewhere inside the paper. Oh, no, this is the first paragraph. Sorry, this really is the first paragraph. I read you the first sentence before. Now let's read the second sentence of the first paragraph of Turing's paper. So although the subject of the paper is mostly about computable numbers, it's most equally easy to define and investigate computable functions. But then still in the first paragraph, he says, I hope shortly to give an account that will include a development of the theory of functions of real variables expressed in terms of computable numbers. Right, so he says, It's this paper is about computable numbers. It's almost as easy to define the notion of computable functions. And I hope someday I will have the time to do that. But that paper never occurred. So this sort of promises a follow-up paper, which never appeared. So you might say, oh, well, we all do that. But then when you get, this is a little video, you continue reading Turing's paper, and he actually gives a definition of computable functions. It's like he wrote that initially, and then he put it down and went back, took a cup of coffee, and came back, cheaper on it, and then he came back to his paper. Now, why not define it? So it actually is, despite this, it's really funny. Despite this, the paper includes a complete definition of what it is for a function to be computable, function of real numbers. He defines it, and rather than showing you his actual version of the definition of a computable function, I'll give you a sort of a modern version, which is that, but this is really what Turing said in his own terms, that a function from the reals from some domain, doesn't have to be the whole reals, but from some domain D, which is subset of the reals, to the reals, is computable. If there's a Turing machine, of course you can say that. If there's an algorithm, a machine with a machine. If there's a machine that takes as input the description of a machine that prints X, or in his mind that computes X, and produces as a result a description of a machine that prints f of X. In other words, Turing's definition, if you have a machine that will compute X in the domain, from any machine that computes some X in the domain, you must be able to obtain another machine that computes f of X. And moreover, going from the first to second machine has to be computable. So Turing's definition, which I have no problem, this is the correct definition, absolutely appropriate. Definition of a computable function of reals is that there would be a machine that can take as input any machine that computes a real number X in the domain, and outputs another machine that computes f of X. That's the definition of a function f to be computable. Again, this is a perfect definition. And now we get to the crux of the problem, which is that with all those definitions of Turing, multiplication by 3 is uncomputable. And that's what I meant by his definitions inappropriate. But that's not all. We'll see later that it's not a wrong definition, but it's inappropriate because it essentially can't do anything with his definition. There's no non-trivial function essentially that can be computed of real numbers with his definition of computable real number and his definition of computable function. There's the problem. Let me prove it to you. Proof is easy, actually. I'm going to become a little bit more technical here. Bear with me for a few minutes if you don't know so much about computability. But the proof is easy if you're familiar with these notions. So let's take an arbitrary, what we call acceptable or standard enumeration of Turing machine. MI is the ith Turing machine. So we need this enumeration to include all Turing machines. And to be effective in the sense that given I and X, there is a universal machine, which was invented during. There's a universal machine that given I and X will compute MI of X. Or will loop forever if MI loops forever on X. So you can stimulate MI on input X by a single machine called universal, that is I and X as input. So that's what it means to be acceptable or standard. And any enumeration will do if this definition. Then I define Ti as the time that MI takes on input 0. Number of steps of a Turing machine. Number of steps to hold on input 0. The ith machine, number of steps the ith machine takes to stop, to hold on input 0. Infinity other ones. And now I define Xi, the real number Xi, as 1/3 minus 10 minus Ti. So for each I, Xi is a real number. So sorry for the confusion. Before Xn was the nth digit of X. Now, xi is the ith real number in a list of real numbers. There's confusion, I'm sorry about that. Right, that's right. So I'm no longer going to use a subscript n to mean the nth digit. So just reset your registers. So, so this is a bit cryptic, but an example will explain it. If the ith machine holds after 6 steps, then xi is 0.33. A third will be just 3 to infinity. But because the ith machine holds after 6 steps, xi has a 2 into the 3, position 6. That's the difference. And what you should notice about this is that if the machine never holds, then xi is a third. If the machine holds at some point, anywhere it holds, then xi is strictly less than a third. Right? So that's what we've seen already. Is what I just said. And also it's easy. Given I, it's easy. Given I and n, it's computing the nth digit of xi. To compute the nth digit of xi, all you have to do is simulate the ith machine for up to n steps. If it holds before n steps, you output a 3. If it holds after exactly n steps, you output a 2. If it has not folded yet after n steps, you output a 3. So this will give you the nth digit of xi. It's computable. Not only is it computable given n, it's also computable given I, so it's uniformly computable. And therefore, xi is printable, even printable given I. So each number xi is printable. Now, how about 3 times xi? Well, 3 times xi is 3 less than 1. If the machine holds, if it holds anywhere, then xi is less than 1. There's a 2 somewhere. Therefore, 3xi is less than 1. Sorry. Xi is less than a third. So if the machine holds, xi is less than a third. Strictly less. Therefore, 3xi is less than 1. But if the machine never holds, well, xi, sorry, just so, but okay, fine. The point was it was an if and only if, not only if. So if the machine holds that first number step, then xi is less than a third, 3xi is less than 1. If the machine never holds, xi is a third, and 3xi is. So xi is less than 1, strictly less than 1, if and only if the ith machine stops, holds on 0. But what's the 0th digit of 3xi, which is the integral part? Well, the 0th digit of 3xi is 1 if 3xi is 1, because 1.000. So the 0th digit of 3xi is 1 if xi is a third, and it's 0 if xi is less than a third. If xi is less than a third, then 3xi is less than 1, therefore the 0th digit integral part is 0. So the integral part of xi, of 3xi, the integral part of 3xi is 1 if and only if the machine never holds. Oops, go on. And therefore it's impossible, it's incomputable, it's undecidable. If you were able to determine the 0th digit of 3xi given I, you would know the ith Turing machine holds or not. And that's undecidable, the Turing improvement. Right, so computing the 0th digit of 3xi is uncomputable, given. And remember the definition of computable function. It should take a description of a machine that computes x, or xi in this case, which you can get from I itself, and give you a description of a Turing machine that computes 3xi, which is impossible. Because if you could do that, you would know if the machine I holds on. Okay. See that before. Okay. So from a So from a description of xi, which you can get from I itself, you cannot get a description of 3xi. Where by description, I mean what I call printable, but what Turing called computable. Here we are. Now you might haven't, well, the first time that I thought about these things, I was only half satisfied because multiplying by 3 is not so hard, actually, if you allow weakly printable numbers. Because if you allow weakly printable, so this is only the strictly printable description. And we don't know if that's what Turing had in mind. If we allow weakly printable, maybe it's different. Because okay, 3 times a weakly printable. With the example I gave, at least, with xi being just a bunch of 3s and 2 somewhere, perhaps. Well, if you want to print 3 times xi, it's very lazy. You just multiply digits by 3. So for a machine that prints xi, which you can get from I, a machine that prints 3 xi this way. Anyway, and here we are. So the contradiction or the impossibility or the uncomputability that doesn't work anymore. If you allow that, if you allow 1 to be printed as 0.9999, then here you are. From I, you can get xi. You can also get 3xi. So that's sort of sad. And we don't know which of the 2 Turing had in mind. We might say, oh, maybe it was not so long after all. Okay. But of course, this would not be valid in the strict version, in the weak version. And that raises the question is multiplied by 3, could it becomes computable in the weakly printable? All we prove that it's not computable is strictly printable. Could we find a way to multiply by 3 in the weakly printable world? And the proof that it's not possible I gave you does not apply. But no, can't either. But it's harder. It's surprisingly harder to prove. It's not so hard. Well, it took us quite a while to find the counterexample, but once you find it, it's sort of obvious as often. However, to prove that what I'm going to show you is indeed undecidable or computable requires a tool that Turing did not have, which is Kleene recursion theorem. So Turing is the total excuse for having not discovered what I'm going to tell you now. But still, let me quickly give you the proof of this statement that even the weakly printable world, multiplied by 3 is still uncomputable. It's very similar. So now TI, remember TI before was the number of steps that machine I took on input 0. Now TI of A is the number of steps it takes on input A. Big deal. And I'm going to define xi in a different way now as a third minus something and plus something. So rather than reading this here, an example says it all. If the machine holds after 4 steps on input 0, then TI of 0 is 4. And I remove, and I subtract 1 in the 4th position. So 3 becomes a 2. But if it holds on input 1 after 9 steps, then I add 1 to the 9th position. So this 3 becomes a 4. And again, given I, it's easy to compute each digit of x. By the way, if the machine holds on 0 and 1 after the same number of steps, then I subtract and add 1, so it becomes a third. If it never holds on either input, then it also would be a third. So it could be a third for 2 different reasons. It could be xi could be a third if the machine never holds either on 0 or 1, holds on 0 and 1 after the same number of steps. But if it holds on at least one of them and not the same number of steps, then what you see is that 3xi is 3 less than 1. Xi is 3 less than a third, and therefore 3xi less than 1 if there's a 2 that comes before them. And this means that the machine holds on 0 before it holds on 1. And conversely, if the machine holds on, not in this case, but if it holds on 1 before 0, then the 4 would be before the 2. Xi will be bigger than a third and 3xi bigger than 1. So this time it's strictly smaller or strictly bigger than 1. depending on whether the machine I holds on 0 before holding on 1, or vice versa. And when I say holds on 0 before holding on 1, that includes holds on 0 as well. It turns out that this is undecidable. But that's not obvious. To prove that this is undecidable, it's not so hard, but it sort of requires Chinese recursion theorem, again, which was not available to Turing. It was invented by Turing, obviously. Obviously, not always. So many algorithms are named by someone who didn't invent it. Anyway, so then I don't have to say more about Chinese theorem, but that's how we get to prove that that's undecidable if a machine holds on 0 before 1 or 1 before 0, and therefore, well, you see, the point is that now the first digit, the 0 digit, I should say, integral part of 3xi is unambiguously 0, 1, because there is no fooling around with infinite sequence of lines. Strictly less than 1, or it's strictly bigger than 1. Therefore, the integral part is exactly 0, exactly 1. No matter what, no matter your definition of how you express numbers. So, all right. So the definition I gave before is not suitable for computation, and of course, and neither is it in the weak version. And of course, Turing was very much interested in defining as computable. So by his own definitions, as I said before, multiplying by 3 is uncomputable, addition is uncomputable. Essentially nothing that's not trivial is computable. Real numbers. Okay, but still we need it. This being said, well, it's just too bad for Turing. We need a proper definition of computable real numbers. And this has been known for a long time. And I'm not inventing anything here. But the first thing that comes to mind is this, I think. In fact, I open a parenthesis. In the 19th century, trying to think about how to define real numbers, forget about computer, just real numbers. Do they exist? It's not obvious, maybe real numbers is no such thing. But mathematicians were trying to define what's a real number. And 2 definitions came up. So I think it's independently. One due to Cauchy, which are the Cauchy sequences, and one due to Dedekind, which are the Dedekind cuts. And they are equivalent, at least if you forget about computability. The equivalent, they define the same set that is all the real numbers. And each of these 2 ways, 19th century's ways to define real numbers, can be adapted to computability issues. And in the end, it will give the same set of computable real numbers. But the one that's usually, I don't know why, but we usually define, we being everyone today, computable real numbers with the Cauchy sequences. So I remind you what it is. A Cauchy sequence is a sequence of rational numbers. I mean, you don't have to be, but in this case, it would. The sequence of y rational numbers because it's easy to describe a rational number with a Turing machine. There's no issue of precision here. Just 2 integers, data ratio. So a Cauchy sequence is a sequence of rational numbers that converge. And there's some convergence criterion that Cauchy thought of. But the most obvious thing which would not work is to say that to define a real number, a computable real number, I'm going to define 2 sequences of integers. So Pn and Qn, which will be computed by 2 different Turing machines. One machine with n gives you Pn in integer this time. The other machine gives you Qn. And then defines a ratio of computable sequence of rational numbers, n over Q, or n. And if that converges to some real number x, we'll say that x is computable. Sounds reasonable. Doesn't work. Doesn't work because someone called Brouwer, in fact, studied these things and called them approachable. And what he proved in his paper is this. It's a nice paper. It's 15 years old. He proved that these approachable numbers, some well-known non-computable number are approachable. In other words, that definition allows you to get uncomputable numbers. And I don't have time to give you examples, but essentially,
What definition?
with the correct definition is coming next. Now, of course, this makes no sense until we know what was the right definition of computer. You're right. But we had it in a moment. But the point is, when Brenner wrote this, everybody agreed it was a computer. So he didn't have to. In fact, it's more interesting because essentially all the numbers that you ever seen in your life, if you remember all about these things, that all the real numbers that are known to be uncomputable, I would say with no exception, maybe I'm wrong, or approachable. In other words, this definition with Cauchy sequences is atrociously bad because it includes all the computable numbers, all the uncomputable numbers you ever thought. And then what Brenner really did interesting, he was able to, of course they exist unapproachable because on the count of the domain. But Brenner was able to build, to actually put his finger on an uncomputable number that's so uncomputable it's not even approachable. But that's not the purpose of my talk, so let's move on. So what we need to do is to, the only thing missing, we need a, so that's even worse than printable. Yes. If you want to define computable, that where's that term? So what we need is a controlled convergence, which in the easiest way would be said this way, that the ratio between the sequence of rationals not only they converge, but in the controlled waveforms, and the distance between the two is less than 10 to minus. So if you add a convergence criterion like this, then it gives a definition of computable real number that we would all agree on today. That's my problems. It's easier to write it this way. It's not exactly equivalent, but almost. And this is a proper definition. It's a proper definition. Okay. That's proper in the sense that this is what we all agree on today. And now I come to what I think is very surprising, equivalence. What I told you so far, let's recapitulate. If you want to define computable real numbers as printable, as Turing did, what do you mean strictly or weakly printable? If you define it that way, then multiplication by 3 is not computable. If you define computable real numbers in the correct way that I just disappeared with, then it's easy to multiply by 3. If you just multiply by 3, you say a sequence of Pn over Qn that converges to x, well, 3Pn over Qn converges to 3x. So you need to do fiddle a bit around it to make it formal, but it's easy to prove the correct definition of computable real numbers. Then multiplication by 3 becomes computable. All right. So in other words, you cannot multiply by 3 a printable number, but you can multiply by 3 a computable number. And there comes the surprise. It's equivalent. A real number is printable if and only if it's computable. And because of this theorem, Turing was not wrong with his definition. He defined the correct set of computable numbers. Because he defined printable numbers, and it's the same as computable. So he was not entirely wrong. It was inadequate because he didn't allow multiplying by 3. But as far as defining the set of computable numbers, which he defined as the printable numbers, that was correct. Well, so is it surprising? It depends on you. Maybe you don't find it surprising. And I don't have time to give you the proof, but a very brief sketch. A very brief sketch is that X be a computable real number. So if it's printable, it's computable, that direction is obvious. That's in the other direction. Let's take any computable real numbers, meaning that you have a controlled convergent Cauchy sequence to X. You're given a machine that does that. Then from that, well, there are two possibilities. Maybe X is an integer divided by power of 10 or not. If it is integer divided by power of 10, then there are two different ways to print it, if you allow weakly printable. But in either case, it's obvious that any real number which is integer divided by a power of 10 is printable. All you have to do is you print the digits. It's obvious. You just print all the digits. You know the integer, so you print all these digits, and then you print zeros. So any number that's an integer divided by power of 10 is printable, even strictly printable. Or x is not an integer divided by power of 10. And then what we have, we have an explicit way to transform the Turing machine that produces this Pn sequence, the Qn sequence, the P over Qn is the Cauchy sequence. We have a way to transform the two machines that produces Pn and Qn into one that will actually print the number x in question. So in other words, we have a constructive way to print any number, any x that is not an integer divided by power of 10, and is given by these two machines that produce Pn and Qn. We have an explicit way to print the digits of Pn over Qn. It's not very hard. It's not totally obvious either, but it's a fact. And the point is that this machine, we have a machine M that will print it. Well, the machine that we can obtain with this, it's a sketch, I'm not showing you how, but the machine that we get, in fact, given P and Q that produce the Cauchy sequence, it is well defined even if X is of the first kind here. It is well defined, but it will look for error in some input. So it doesn't work. So you see, it's a non-constructive argument that either X is of the first or the second kind. If it's of the first kind, then you can print it this way. If it's the second kind, then you can print it that way. So either way you can print it, but it's non-constructive. So it's equivalent, but what happened to this apparent paradox, as you might have understood already, is resolved because no computable process can map the computable description of a real number to its printable description. So each computable number is printable and vice versa, but you cannot go from a computable description to its printable equivalent. So that transition isn't computable. That's how it is. And so this equivalence is true, but not constructively valid. So it's not true if you're a constructivist, actually. And I will tell you a bit more about this in a few minutes. I've been talking for an hour already. I will need a few more minutes to tell you about that issue, which I think is really, really interesting. But now I should tell you that Turing, this is the paper I talked about from the beginning, the 1936 paper. Actually published in 37, but it's written in 36. We all talk about 1936 paper of Turing. It was published in 1937. And well, it turns out that everything I told you essentially, I'm sorry, but I wasn't the first there. Turing thought about that a year later. So 1 year later, Turing published a correction. Which was sort of heartbreaking when we realized that how can you possibly publish our paper? Turing was there before us. Oh well, shit. But I still don't know how we managed to publish it, but we did. This is the correction. This is the correction. In the correction, Turing said that there are some statements that should be modified, although they're not false. They're not false because, as I said, he defined computable numbers, and what it is defines the computable numbers. So it's not false. Maybe it should be modified, maybe. And then he goes on, this is going to be a bit more technical, but I'll try to do it quickly. And then in his correction, he says that some difficulty arises. He doesn't quite say what. He says there are some difficulties. I don't think he says, well, something isn't. What sort of difficulty? But obviously he had understood that nothing is computable. No function is computable. So what he did then is that here's another way. These are the Dedekind cuts. The computable version of the Dedekind cuts is here. I won't go into detail of that, but he says that if a real number is defined in this way, then clearly this deserves to be called computable. Again, it's a computable version of the Dedekind cut. And so he said that these numbers are computable. And of course, it still needs printable. What he did not do in his correction is, well, I'm sorry, please replace my definition of computable by this instead. Because this would have been the proper definition of computable, actually. But instead of saying that, he says, well, these numbers are computable. You would expect them to be computable, but they are. They are. By which he means they're printable, because he didn't change his definition. Very strange. And then, so in other words, it means that all computable numbers are printable. That's what he says here. It's correct. Doesn't give the proof. Doesn't give the proof, but he says a proof may be given. Look, it's just a note I didn't prove. It's correction. It's on a few pages. What do you expect? He says a proof may be given, but it doesn't give us the proof. But it gives us an idea, because the proof will involve the principle of excluded middle, which can only mean, and here I'm just guessing, I don't know, not in his mind, but I can only guess that what he meant by this is that the proof involves a statement of the sort, either x is an integer divided by a power of 2, because it was in binary, or it's not. And in either case, the computable number is printable, which he called computable. So the only possible, I cannot think of any other explanation for this sentence that he wasn't actually having the same proof as we have. But he didn't get it. And then he goes on to say, and therefore, so Turing's proof is not, so this means that Turing's proof, which we will never know, is not constructively valid. Neither is my proof. And then he goes on saying that statement A is that, so this statement A is all computable numbers are printable. That's what statement A says. Statement B says that statement B would say that it's possible. Dn is the description number of Turing machine. So this says that if you have a Turing machine number, you have a Turing machine that computes or that prints. If you have a machine that if you have a machine that computes a real number with the right definition, if you had one, then you could find a machine that computes it, where computing here means prints. So statement B would be that it's false, that you can go from statement B is you can go from computable to printable. That's statement B. And then he says that B is false if you want to do it constructively. So what he says here is that not only his proof is not constructive, but saying that B is false means that the statement is inherently not constructive. Not just his proof. In other words, it's not possible to prove that constructively, which is indeed the case. So he had almost everything there. Almost everything I told you was there in the correction. And then he restricts, but he could only prove that it's not constructively valid in the case where you restrict to strictly printable. So he admits that for the weakly printable, he does. Again, normal, because he didn't have KRG, linear regression theorem. All right. So it's only in the strictly printable world that he says that. We don't have his proof, but we can assume that is essentially the proof I have. All right. Okay, let's not spend time on this one. Here, the very last paragraph is correction. I just want to show you that, and now he gives another definition of constructive numbers, of computable. Instead of, he proposes it, he said, well, perhaps we could define, instead of using the Nitkin cuts, which would be beautiful, as he did just a few pages before. Now he says, oh, well, if you really want to define computable numbers in the way that you do arithmetic, well, take that definition. No clue in it. But that's okay. All right. So the last few minutes, I want to tell you about constructivism, which I think is a very, very interesting issue. And I could give a whole talk about that. Which is that this definition, I said, is a proper definition, and it's the only way. And we don't have another one. Well, the one that they can cut is equivalent, but we all agree, we in the community, we all agree on what it means for a real number to be computable. And it means what I told you, not what Turing told you. But it has a problem. But it's an unavoidable problem. And for this, let me refer to this person, probably the greatest Dutch mathematician of all time, Brouwer. So Brouwer, very, really an amazing person. And Brouwer, this picture is taken in the building of the Dutch Academy of Sciences in Amsterdam. So Brouwer is best known for two things. One is for intuitionism, which is a form of constructivism. And the other is for his fixed point theorem. Now, David Hilbert admired the fixed point theorem and despised intuitionism. And perhaps one reason why he liked the fixed point theorem so much is that it's hard to find a more non-constructive theorem than Brouwer's own fixed point theorem. But the history, as I understand it, and I may be wrong, so sorry, but as I understand the history, Brouwer proved the fixed point theorem at some point in his life, before he became a constructivist. And then his mind evolved, and he began to decide that mathematics should be constructive. And I don't have time to tell you what it means. But things like, if you want to prove that A or B is true, or P or Q, if you want to prove P or Q, then you have to prove P or prove Q. Okay? And if you don't know if it's P or Q that's true, then you don't know that P or Q is true. So this is the law of the excluded middle that Turing mentioned. In what we call classical mathematics, not non-constructive, non-constructive, well, usual stuff. You are allowed to prove a statement by contradiction. If what you want to prove is false, then you derive a contradiction. Therefore, what you wanted to prove is correct. That is not constructively valid. For constructivists, if you want to prove that there is an x such as f of x, you have to exhibit x. Or at least give a machine that will compute x. Not just prove that if x didn't exist, then there would be a contradiction. So that's what constructivism is all about, in a nutshell. And all sorts of, and you get all sorts of weird theorems, such as it's no longer true that a quadratic equation has only two solutions. Again, you can have more. It's not true anymore that a bounded sequence of increasing numbers converges. That's no longer true. There are all sorts of really neat stuff in non-constructive, so in constructive mathematics. But since my time is up, I will just give you two examples which are relevant too. Yes?
The statement that to prove pure, I mean, if you prove by contradiction,
Yes.
it's different than the statement you cannot prove pure Q if you cannot prove either. Because, I mean, I can prove that either the real numbers are RF1 or they're not RF1, but I cannot prove either of the statements.
I did not mean to say
So I
the
cannot
equivalent.
prove it by contradiction.
No, I did not say the equivalent. I'm saying that a constructivist will refute, will not accept either argument. I'm not saying they are the equivalent. They're related. Anyway, so the story that, as I understand it about Brouwer, is that he proved that theorem, but before publishing it, he moved on. His mind moved on to constructivism, and therefore he knew that his theorem, the fixed point theorem, was bullshit. I mean, it was complete. Suddenly, it went against everything that he believed in. But he published it anyways because he knew it would get fame and fortune from that. And indeed, Hilbert was very pleased. But after that, he clearly moved out. I mean, he did not disown it, but he would not accept this proof anymore. All right. So to make a story short, I said that the standard definition of computable number has problems, and I'm just going to tell you two of them. And we're going to end by going back to Turing, full circle. Well, it's all due to Brouwer's most amazing theorem, which is not a fixed point theorem. Brouwer's most amazing theorem, known as the continuity theorem, says something, and what you're going to see is not a typo. All total real functions are continuous on the unit interval. It sounds crazy, right? But he proved it. Brouwer proved that all continuous functions on the closed, the unit interval is a closed 0, 1. So in 2, 0, and 1. It was more general, but it's a simple version. Any function of the real numbers whose domain is a closed interval 0, 1, and which is total, is continuous. Crazy. But the explanation is that for should I say normal people, there are non-continuous functions, of course, but all of them are uncomputable. And for Brouwer, uncomputable functions simply don't exist. There we are. So no function exists that is not continuous on the interval. Because what these crazy other people say about non-continuous functions, well, these things are not computable, therefore they don't exist. So whether or not you agree with Brouwer, you cannot, Brouwer theorem is correct. This statement is correct. This statement is correct. But you may not agree that non-computable functions don't exist. So to make a story short, we're going to just rewrite this in more classical terms, where classical is opposed to constructive and not quantum. I'm going to rephrase this in the following way. And this theorem is correct for a classical mathematician. All total computable real functions on the interval are continuous. Just add computable to this statement, add computable, and it becomes fine for everyone. Redundant for Brouwer, but still good for me too. And therefore, look at this function. F of x is 1 if x is 0 and 0 otherwise. How can it be more so this is clearly not continuous. This is an example of a function from the unit interval that's not continuous, yet it exists for us. If we're not going, but Brouwer's theorem implies that it is discontinuous, it is total, it is on the unit interval, and therefore it's uncomputable. And what this means is that testing if x is 0 is undecidable. No algorithm given a real number x meaning given a machine that computes x, can tell you if x is equal to 0 or not. It's annoying. It's very annoying. But there's no way around it. Nobody has ever thought of an alternative definition of computable real numbers that would make equals to 0 decidable. It's a bummer, but we'll finish with it. But let me give you the other example, which is my final slide essentially. Look at this one. You might remember this one. This is how Turing went from a real number between 0 and 1 that was computable to an arbitrary real number between plus and minus infinity. That's the formula that Turing used. And you might remember that this formula doesn't work when x is 0, 1, there's no tangent of pi over 2, or plus or minus pi over 2. So this formula doesn't work when x is 0, 1, and therefore Turing said, well, we'll take a special case. If x is 0 and 1, then f of x is 0. So this formula transforms any real number between 0 and 1 included into a real number in a whole range of real numbers. And that's how Turing defined a computable real number without restriction between 0 and 1. So it looks like this, remember? He had to add 2 exceptions here. Well, you see me coming. That's not continuous. Therefore, it's not computable. So it's really ironic that Turing's idea to define a computable real number, not just between 0 and 1, is through an uncomputable function. And it's not uncomputable on printable numbers. It's uncomputable on computable numbers. It's worse. Well, computed. I have great admiration for Turing. He's my hero. But look, some people make mistakes, and his correction was not enough. And others, like Shannon, when Shannon defined information theory in his 1946 paper, it was perfect from beginning to end, not a word to change. But he cheated because he worked on it for tens of years in secret. Before publishing, I think. I was told, I don't know if it's true. And, well, okay, so, but you just keep trying. All right. Thank you.
We're gonna take a couple of questions. Okay.
So, all right, so
It's better with my piece.
all right, so it looks like the definition of computability somehow depends on the representation of the numbers using Turing machines.
Yeah.
So the decimal expansion is not quite right, and the Cauchy sequence of the Degin cuts make it right. Are there other representations which would be even better, perhaps?
Well, that's what I'm asking.
Oh, I see.
As I said, why don't you take it? The Cauchy sequences or the computable version of Dedekind cuts that will define the same real numbers and cannot test if it's equal to 0 either way. So and I've never seen it might be that there's no definition of computable real numbers that would allow testing for 0.
Okay, I think we are already running out of time. If there is really pressing last question, maybe not, let me maybe. Yes, close this often that you spoke up for our appreciation.
Thank you.
Thank you very much.